And now, if you would kindly settle beneath the covers, let the weight of the day slip gently from your shoulders and allow your breathing to slow. We shall embark together on a journey of almost inconceivable distance. We begin here, in the quiet familiarity of a December night. Somewhere on the cool outer rim of a spiral galaxy we have long called home. Above us, the winter sky glitters with a faint silver river of light, the Milky Way itself, arching from horizon to horizon like a frozen exhalation of starlight. Yet tonight, dear listener, we are not content to remain upon this comfortable suburban shore. Tonight, we shall turn our gaze inward, and with the unhurried patience of deep time, we shall drift together toward the very center of our galaxy, 27,000 light-years inward, through the slow-turning spiral arms, past the glowing nurseries of newborn suns, past the ancient globular clusters that hover like fireflies around the disk, until at last we approach the dark and brooding heart that has haunted astronomers for centuries. Imagine, if you will, that we are weightless, suspended in the perfect silence of the vacuum. The Earth has fallen far behind us now, a pale blue dot lost among the Orion Arm's scattered jewels. Ahead, the density of stars begins to increase, almost imperceptibly at first, then with gathering insistence. The sky, which once seemed comfortably spacious, now crowds with light. Suns of every temperature and temperament drift past us in their millions. Red giants swollen to the size of earthly orbits, white dwarfs no larger than our own planet, yet heavier than the sun, yellow dwarfs like our familiar Sol, and here and there, the fierce blue-white glare of the most massive stars, burning through their hydrogen with reckless extravagance. We move steadily inward, and the galactic disk thickens around us. Dust lanes, those vast somber clouds of interstellar soot, begin to braid themselves across our view, obscuring great stretches of the star fields and lending the scene a somber, almost cathedral-like dimness. Onward we glide, at a speed that would once have been thought impossible. Yet here, in the tranquility of imagination, we feel no haste. The constellations we once knew have long since dissolved into anonymity. The familiar patterns of Cassiopeia, of Orion, of the Plough, are quite unrecognizable when one is immersed within the galaxy, rather than gazing upon it from without. Instead, we find ourselves surrounded by a continuous shimmer of starlight, as though we have fallen into a snowstorm composed entirely of diamonds. And still, the center calls us. The density continues to rise. 10,000 light-years from the sun, 20,000, 25,000, until at last, some 26,800 light-years from the quiet bedroom we lately departed, the character of the heavens changes utterly. Here, in the innermost kiloparsec, the stellar density is almost beyond comprehension. In the quiet suburbs where Sol resides, one might travel a dozen light-years before encountering another star system worthy of note. Here, in the central bulge, stars are separated by mere fractions of a light-year. In the very core, by scant light weeks. Were a planet to exist in these regions, and we have no evidence that any does, its night sky would blaze with 1,000 suns brighter than Sirius, and the concept of darkness would be entirely unknown. Yet paradoxically, as we draw nearer still, a curious obscuration begins to dominate the view. Vast molecular clouds, colder than the space between the stars and laced with complex organic chemistry, lie in great ragged curtains across our line of sight. Through the visible spectrum, These clouds are almost perfectly opaque, and for centuries they concealed from human eyes the true nature of what lay beyond. But we, dear companion of the night, are not limited to the light that human eyes perceive. We may avail ourselves of every messenger the cosmos has seen fit to provide: the radio whisper, the infrared glow that penetrates dust, the relentless pierce of X-ray and gamma-ray photons born in temperatures of millions of degrees. And so, as we drift together through these final few hundred light years, let us dim the glare of ordinary starlight and allow longer wavelengths to paint the scene anew. There, directly ahead, a compact source of extraordinary power begins to resolve itself. It is no larger than the orbit of Mercury, yet it outshines, in radio waves, the entire surrounding galaxy of 400 billion suns. Astronomers, with their customary restraint, have named it Sagittarius A star, SGR A star. To our modern eyes, it is the signature of a supermassive black hole, 4 million times the mass of the Sun, wrapped in a glowing torus of accretion and orbited by a retinue of the most massive and luminous stars in the galaxy. Yet this understanding, so calmly accepted today, is the culmination of a detective story that began more than 2 centuries ago, when the tools at humanity's disposal were little more than a polished mirror and an observant eye. Let us therefore pause in our inward drift and allow the centuries to unroll gently before us like an old parchment map. It was in the spring of 1764 that a French comet hunter by the name of Charles Messier, working from a cramped observatory atop the Hôtel de Cluny in Paris, first turned his small refracting telescope toward a peculiar patch of the summer Milky Way in the constellation Sagittarius. Messier was engaged in his noble labor of cataloguing objects that might be mistaken for comets, nebulous patches that remained stubbornly fixed among the stars. And on the 3rd of June, he noted in his meticulous hand what would become the 66th entry in his now famous list: Nebula without stars in Sagittarius, very faint. We know today that Messier had glimpsed the integrated light of the central star cluster, scattered and dimmed by 28 magnitudes of visual extinction, more than a millionfold obscuration by dust. He could not have suspected that he was looking toward the gravitational heart of the galaxy itself. 18 years later, in the soft English summer of 1782, William Herschel, then freshly appointed King's astronomer and still basking in the glory of his discovery of Uranus, began his systematic stargaging of the heavens. With his great 20-foot reflector at Slough, Herschel counted the number of stars visible in different directions, assuming, quite reasonably for the time, that all stars were roughly equally bright, and that he was therefore mapping the extent of the stellar system in depth. In most directions, the counts fell away with distance, but towards Sagittarius, they remained stubbornly high. In his 1785 paper to the Royal Society, he wrote with characteristic understatement, "The Milky Way begins to be crowded with stars in a considerable degree about the middle of Sagittarius, and here the gauging seems to lose all kind of regularity." Herschel concluded that the stellar system must be vastly extended in that direction, though he placed the Sun near the center of what he imagined to be a flattened grindstone of stars. The true picture that we reside far out in the disk and that Sagittarius marks the direction of the center would not emerge for another century and a half. As the 19th century unfolded, spectroscopy began to reveal the motions of stars through the Doppler shift of their light. In the early years of the 20th century, the Dutch astronomer Jacobus Kapteyn, working from photographic plates taken at the Cape of Good Hope, attempted a more sophisticated reconstruction of the galaxy. Yet even Kapteyn, hampered by the unknown effects of interstellar absorption, placed the Sun near the center of a system only some 10,000 light-years across. The true scale and our peripheral position would be established only when a young American astronomer named Harlow Shapley turned his attention not to the obscure disk, but to the globular clusters that hover above and below the plane like a swarm of bees around their hive. Between 1914 and 1919, using the 60-inch and later the 100-inch reflector on Mount Wilson, Shapley measured the periods of RR Lyrae variable stars within these clusters. Because Henrietta Leavitt had lately established the period luminosity relation for Cepheid variables, and RR Lyrae stars obey a similar law, Shapley could convert observed period into intrinsic brightness and thence into distance. To his astonishment, the globular clusters were not centered on the Sun, but on a point far away in Sagittarius, fully 30,000 light-years distant by his initial calibration, remarkably close to modern values. In a series of papers culminating in 1918, Shapley announced that the Sun lay near the edge of a galactic system of truly colossal extent, with the center marked by the rich star fields his predecessors had noted. The solar system, he wrote with quiet audacity, is far from the middle of the great stellar universe, being situated near one of the borders. Yet even Shapley could not pierce the veil of dust that concealed the center itself. For that, astronomy would have to await a discovery made not with optical glass, but with copper wire and thermionic valves. In 1932, a young Bell Telephone Laboratories engineer named Karl Jansky was tasked with investigating sources of static that might interfere with the new transatlantic radio telephone service, using a large rotating aerial array at Holmdel, New Jersey, a contraption that looked for all the world like a fairground ride. Jansky identified 3 distinct sources of noise: local thunderstorms, distant thunderstorms, and a steady hiss whose direction changed sidereally day by day. In his 1933 paper to the Institute of Radio Engineers, he reported with admirable caution that the maximum intensity of this third component arrived when the antenna pointed toward the constellation Sagittarius. The center of the galaxy, it seemed, was a source of radio emission. The discovery attracted polite interest, but little immediate follow-up. Jansky himself was reassigned to other projects. It would fall to an amateur, in the truest and noblest sense of that word, to build the first instrument dedicated to the new science of radio astronomy. Grote Reber, a radio engineer from Wheaton, Illinois, constructed in his back garden during 1937 a 31-foot parabolic dish of galvanized iron mounted on a pivoting frame that allowed it to scan the sky in declination. Working alone, often at night to avoid interference, Reber produced in 1940 the first radio maps of the sky at 160 megahertz. The brightest feature by far was an extended source centered on Sagittarius. In a 1944 paper in the Astrophysical Journal, he noted that the emission reached its greatest intensity at right ascension 17 hours 42 minutes, declination minus 29 degrees, coordinates that placed it squarely in the direction Shapley had identified as the galactic center. Through the war years and into the 1950s, larger radio telescopes came into operation, first at Jodrell Bank, then at Parkes, and in the Netherlands at Dwingeloo. Interferometry allowed ever finer resolution. By the early 1970s, Bruce Ballack and Robert Brown, using the Greenbank 4-element interferometer, succeeded in resolving a remarkably compact source within the broader Sagittarius emission. Their object, measured at a wavelength of 3.7 centimeters, was smaller than 10 arcseconds across, less than 1,000th the width of the full moon, and lay at the very heart of the galactic plane. In a terse internal memorandum dated February 13, 1974, Brown suggested the name Sagittarius A star to distinguish this intense point source from the surrounding complex of thermal gas and supernova remnants, collectively known as SGR-A. The asterisk, borrowed from the notation for excited atomic states, would prove singularly appropriate. By the close of the 1970s, very long baseline interferometry had shrunk the apparent size of SGR-A to mere milliseconds, thousands of times smaller than the resolution of the human eye. At a distance of 8 kiloparsecs, this corresponded to a physical diameter no larger than the orbit of Mars. Yet the radioluminosity remained prodigious, and the source exhibited variability on timescales as short as minutes. Whatever resided at the dynamical center of the Milky Way was clearly both extraordinarily compact and extraordinarily energetic. As infrared detectors, cooled by liquid helium, began to peer through the obscuring dust in the 1980s and 1990s, astronomers on Mauna Kea and in the Atacama discovered a dense cluster of hot, massive stars orbiting a common focus at speeds of thousands of kilometers per second. Reinhard Genzel in Germany and Andrea Ghez in California led teams that tracked these so-called S-stars over decades, mapping their orbits with ever greater precision. The focus of these Keplerian ellipses coincided exactly with the position of SGR-A star. By 2008, the star S2 had completed a full 16-year orbit, reaching a periapsis velocity of nearly 3% the speed of light. The only object capable of providing the required centripetal acceleration within the observed volume was a mass of approximately 4 million solar masses compressed to a radius smaller than the orbit of Mercury. And so, dear listener, as our inward journey nears its climax, we find ourselves suspended mere light hours from the darkest point in the visible galaxy. Around us whirl the innermost stars, luminous blue stragglers and Wolf-Rayet giants, shedding their outer layers in fierce stellar winds that collide and shock heat the surrounding medium to X-ray temperatures. Closer still, a dim red torus of molecular gas and dust, warm to a few hundred Kelvin, encircles the center like a cosmic smoke ring. And at the very heart, invisible yet inescapable, lurks the supermassive black hole we have pursued across centuries of discovery. But before we cross the final threshold, before we contemplate the event horizon itself, the glowing accretion flow, the relativistic jets that may or may not be born here, let us simply rest a while in the knowledge that we have arrived. But before we cross the final threshold, before we contemplate the event horizon itself, the glowing accretion flow, the relativistic jets that may or may not be born here, let us simply rest a while in the knowledge that we have arrived. And here, in the hush before the final revelation, we may allow our thoughts to drift, unhurried, through the long history that brought us to this point then, almost imperceptibly, we let that history dissolve into the deeper silence that surrounds us now, here, only a few light hours from the place where light itself surrenders. The year is no longer 1974, nor 2008, nor even the gentle 21st century of our childhood. The calendars of Earth have become irrelevant. We hover in the year 2019 of the Common Era, and then in 2022, and again in the quiet spring of 2024 and the early winter of 2025, years in which humankind, with exquisite patience, finally trained upon Sagittarius A, an instrument vast enough and delicate enough to see what no eye nor any single telescope could ever hope to resolve. Picture, if you will, an array of radio dishes scattered across the surface of our pale blue dot, like the petals of some immense metallic flower. The South Pole Telescope, standing alone upon the high Antarctic plateau, where the air is thin and astonishingly transparent to millimeter waves. The mighty phased array of ALMA, 5,000 meters above the Atacama Desert, its 66 antennae gleaming like silver mushrooms beneath an indigo sky. The submillimeter telescope on Mount Graham in Arizona, the IRAM 30-meter dish on Pico Veleta in Spain, the James Clerk Maxwell telescope, and the submillimeter array upon the gentle summit of Mauna Kea, the large millimeter telescope in Mexico, and, for the later campaigns, the brand new Greenland telescope, hauled piece by piece across the ice and erected within sight of the aurora. These instruments, separated by thousands of kilometers, were linked together by the most precise atomic clocks humanity has ever built, hydrogen masers stable to 1 second in 10,000 million years, and by corridors of fiber optic cable and dedicated satellite uplinks, until, for a few precious nights in April 2017, and again in 2018, and yet again in 2022 and 2024, they functioned as a single telescope with an effective diameter equal to that of the Earth itself. The Event Horizon Telescope, as this virtual colossus was named, observed at a wavelength of 1.3 millimeters, 230 gigahertz, chosen with care because it is one of the few windows through which the galactic center's obscuring dust becomes almost transparent, and because it is close to the peak of the emission from the hot plasma that swirls in the black hole's immediate grasp. For 10 nights, the telescope stared, unblinking, collecting petabytes of raw data that were etched onto racks of hard drives, sealed in Pelican cases, and flown by commercial airliner to central correlator facilities at the Max Planck Institute for Radio Astronomy in Bonn and at MIT's Haystack Observatory in Massachusetts. There, the terabytes were coaxed hour after hour into coherence until at last, on the morning of the 10th of April 2019, the collaboration's imaging teams looked upon the first resolved portrait of a black hole's shadow. It was not our black hole, not yet. The first image released to a waiting world belonged to Messier 87, the supergiant elliptical galaxy in Virgo, whose active nucleus is powered by a black hole of 6.5 billion solar masses. Yet the techniques perfected upon M87 were the rehearsal for the far more intimate and far more difficult observation of Sagittarius A star, where M87's shadow subtended some 40 microarcseconds. The predicted shadow of SGR A star would be only half as large, a mere 20 microarcseconds. and the plasma around our own black hole is far more turbulent, changing on timescales of minutes rather than days. The Earth's atmosphere, even above the finest sites, introduces phase errors that must be painstakingly unwound. The interstellar plasma scatters the incoming wavefronts in a manner that had to be modeled and removed. It was, in the understated words of the collaboration, an exceedingly challenging target. Nevertheless, on the 12th of May 2022, in press conferences held simultaneously in Washington, Munich, Tokyo, Shanghai, Taipei, and Santiago, the Event Horizon Telescope collaboration revealed to humanity the first direct image of the supermassive black hole at the center of our own galaxy. There, upon screens around the world, glowed the now iconic ring, a golden torus of emission, slightly squashed into an oval by the black hole's rotation, surrounding a darker annulus, and at its very heart, the perfect circular absence of light we call the shadow. The bright ring measured 51 micro-arc-seconds across, give or take half a micro-arc-second, corresponding at the precisely measured distance of 8,178 parsecs published by the Gravity Collaboration in 2019, to a shadow diameter of approximately 10 million kilometers, or roughly 12 times the radius of the event horizon itself, in 6 papers published simultaneously in the Astrophysical Journal Letters, Volume 930, Issue 2, May 2022. The collaboration laid out the meticulous case. Paper I presented the image itself and the 4 independent imaging algorithms, regularized maximum likelihood, clean, and 2 variants of sparse modeling that all recovered the same robust features. Paper 2 detailed the calibration and the heroic efforts to mitigate interstellar scattering, which would otherwise have blurred the image into uselessness. Paper 3 compared the observed morphology to a vast library of general relativistic magnetohydrodynamic simulations, finding that the data favored a magnetic flux-threaded accretion flow viewed at an inclination of approximately 160 degrees, nearly face-on with the black hole's spin axis pointed almost directly toward Earth. Paper 4 placed stringent constraints on alternatives. No cluster of neutron stars, no boson star, no exotic gravastar could reproduce both the compactness and the luminosity. Paper 5 measured the mass anew, refining the value to 4.10, plus or minus 0.0, 6 times 10 to the 6th solar masses, in exquisite agreement with the 4.10, 0, plus or minus 0.034 times 10 to the 6th solar masses derived from the stellar orbits by Du and collaborators in 2019 and confirmed by the Gravity team in 2023. Paper 6 examined the faint, persistent emission inside the ring and concluded that it is consistent with synchrotron radiation from a radiatively inefficient accretion flow at a mere few % of the Eddington rate. And so, in the calm language of science, the case was closed. The dark heart of the Milky Way is indeed a black hole, 4,100,000 times the mass of the Sun, spinning at between 50 and 90% of the maximum rate permitted by general relativity, and currently dining rather abstemiously upon the thin gruel of interstellar gas that trickles inward through the central molecular zone. Yet the story did not end in 2022. The Event Horizon Telescope is not a single photograph, but an evolving motion picture. In April 2024, the array observed again this time augmented by additional stations and improved correlation algorithms. Early results presented at the 244th meeting of the American Astronomical Society in Madison, Wisconsin in June 2024 and published in 2025. Astrophysical Journal Letters, Volume 957, revealed that the bright emission ring is not static. Over timescales of hours, the brightest spot migrates around the ring, tracing the orbital motion of hotspots in the accretion flow at radii only a few times the event horizon. These orbiting crescents match almost perfectly the predictions of GRMHD models in which the flow is turbulent and magnetically dominated, and they allow, for the first time, an estimate of the black hole spin parameter directly from the image morphology. A equals 0.84 plus or minus 0.10, confirming the high spin inferred from the stellar orbits and from X-ray reflection spectroscopy of the accretion disk flares. Even as these words drift gently across the quiet bedroom, the 2025 observing campaign, conducted in March and April of this year, has just concluded. The Greenland telescope is now fully operational at 1.3 millimeters. The Kitt Peak 12-meter dish has been added in Arizona, and the Africa Millimeter Telescope in Namibia is expected to join the array in 2027. Correlation is still underway, but leaked horizon-resolved polarimetric images whispered about at the Black Holes on the Horizon conference in Reykjavik this past September suggest that we are on the verge of mapping the magnetic field lines threaded through the accretion flow, and perhaps even of detecting the photon ring, that faint, razor-thin echo of light that has orbited the black hole multiple times before escaping to our telescopes. When those images are finally published, likely in the spring of 2026, they will represent the clearest view yet of space-time in its most extreme manifestation. For now, though, let us simply rest with what we have already been granted. We drift together in the soft radio glow of that golden ring, 51 million kilometers across, encircling a darkness so absolute that no photon, no messenger of any kind has ever returned from within. The shadow's edge marks the boundary where stable photon orbits cease to exist. Inside lies the event horizon itself, a sphere some 24 million kilometers in diameter, twice the distance from Earth to Moon, across which the river of time slows, stretches, and finally stops for any observer who dares to cross. And yet, paradoxically, this most violent and absolute of objects is also among the quietest, unlike its cousin in M87, which devours entire suns and exhales relativistic jets visible across intergalactic space. Sagittarius A star is almost dormant. Its bolometric luminosity is less than 10,000 times that of the Sun, a mere whisper compared to the 10 trillion solar luminosities it could, in principle, emit if matter fell freely onto it. The accretion flow is hot, tenuous, and magnetically arrested. Much of the infalling gas is driven outward again in turbulent winds before it ever reaches the horizon. In the words of the 2022 EHT Paper 3, SGR A star is presently in a low luminosity state characteristic of a radiatively inefficient accretion flow, with strong outflows removing most of the available angular momentum and energy. So here we float, suspended in the hush that surrounds the quietest monster in the galaxy. Around us, central star cluster glimmers, IRS 16SW, IRS 33E, the luminous blue variables, and the tight whirl of S stars, of which S4716, discovered by Peisker and colleagues in 2023, now holds the record for the fastest known orbit, completing one circuit every 4 years at a periapsis distance of only 150 astronomical units. Beyond them, the circumnuclear disk, a warped and clumpy ring of molecular gas extending from 2 to 7 parsecs, rotates slowly like a cosmic Catherine wheel, and inward of everything, closer than any star, closer even than the innermost stable circular orbit for non-spinning matter, the black hole waits, patient as entropy itself. Let your breathing slow now, dear companion of the night. Let the golden ring blur gently at the edges of perception. Feel the immense stillness that resides at the center of all this motion, the perfect calm that is the eye of the galactic hurricane. We have traveled 27,000 light years to arrive here, and having arrived, we discover that there is, after all, very little to disturb our rest. The monster sleeps, the stars wheel in their ancient dance, and the darkness at the heart of the Milky Way keeps its secrets with the same serene indifference it has shown for 10 billion years. And yet, in the last fleeting quarter century of human observation, that same darkness has begun, ever so gently, to stir. We remain here, suspended in the velvet hush just beyond the photon orbit, where the golden ring of the event horizon image still glows softly in memory. But let us now lower our gaze a little. Let it drift outward from the perfect shadow to the region where light is still free to come and go as it pleases, to the innermost few light days, where a handful of young and reckless stars perform the most exquisite ballet ever witnessed around a supermassive black hole. Imagine, if you will, that we are perched upon an imaginary platform perhaps half a light year above the galactic plane, looking down upon the central parsec as though it were a great darkened amphitheater lit only by the blue-white glare of its performers. At the very center sits the invisible 4 million solar mass point, marked now only by the faint radio whisper of Sagittarius A star. Around it, in a volume no larger than a sugar cube placed beside the sun, orbit several dozen massive stars whose individual motions have been tracked, night after patient night, by the mighty 10-meter mirrors of the Keck telescopes in Hawaii and the 4 8-meter units of the Very Large Telescope high upon Cerro Paranal in Chile. These are the S stars, so called because they move within the central arc second of Sagittarius, and among them are the swiftest objects ever to trace closed orbits under the influence of a single gravitational source. Let us linger first with a star that, for 2 decades, has been the prima ballerina of this extraordinary troupe, S0-2 in the American naming convention, or S2 in the nomenclature preferred by our European friends. Discovered in the late 1990s by the UCLA Galactic Center Group under the leadership of Andrea Ghez, and by the rival, though always courteous, team at the Max Planck Institute für Extraterrestrische Physik, led by Reinhard Genzel. S2 is a perfectly ordinary B-type main sequence star of perhaps 15 solar masses, burning with the serene blue brilliance of youth. Yet its orbit is anything but ordinary. Every 16.00 years, it sweeps around the black hole in a highly eccentric ellipse, E equals 0.884, reaching a periapsis distance of only 120 astronomical units, barely 17 light hours, or 4 times the radius of Neptune's orbit around the Sun. At that closest approach, which last occurred in the spring of 2018 and will next grace our instruments in the summer of 2034, S2 accelerates to almost 7,700 kilometers per second, more than 2.5% the speed of light. For a few brief weeks, it becomes the fastest known macroscopic object in the entire galaxy. The monitoring of S2 has been a labor of almost monastic devotion. Night after night, year after year, the two great teams have employed adaptive optics, those miraculous deformable mirrors that undo the twinkling caused by Earth's atmosphere, to obtain diffraction-limited images at near-infrared wavelengths, where the dust is least obstructive. Speckle holography in the early years gave way to full adaptive optics, and then, from 2016 onward, to the beam combiner instrument Gravity, which unites the light from all four VLT telescopes to achieve an astrometric precision of 10 microarcseconds, the width of a human hair seen from 10 kilometers away. With such precision, it became possible not merely to plot the orbit, but to test, for the first time in the strong field regime, the predictions of Einstein's general theory of relativity itself. In the summer of 2018, as S2 plunged toward periapsis, the world's astronomers held their breath. Newtonian gravity predicted a perfect rosette, an ellipse that would precess neither forward nor backward. General relativity, however, demands that the argument of periapsis advance by 12 arc-minutes per orbit, an angle equivalent to the width of a grain of rice held at arm's length. And so it proved. In a series of papers published between 2019 and 2020, most notably Abuter et al. In Astronomy and Astrophysics, Volume 636, April 2020, and the UCLA companion paper by Doe et al. In Science, October 2019. Both teams reported a measured redshift of the star's K-band light consistent with the combined transverse Doppler and gravitational effects to within 10%, and an advance of periapsis that agreed with Einstein's prediction to better than 1%. The black hole had passed its most stringent laboratory test, with colors flying. Yet S2 is no longer the undisputed record holder. In 2014, the Gravity Collaboration announced the discovery of an even closer star, S0-102, or S4711 in European numbering, which completes an orbit in only 11.5 years. And in the past 5 years, the census has grown richer still. As of the 2024 data release, Gravity Collaboration, Astronomy and Astrophysics, Volume 692, October 2024, no fewer than 42 S-stars have well-determined orbits, and the fastest of them all is now S4716, discovered by Florian Peisker and colleagues at Cologne, a star that skims to within 100 astronomical units of the event horizon every 4 years, reaching velocities in excess of 8% the speed of light. One scarcely knows whether to marvel more at the audacity of nature or at the patience of the observers who have tracked these faint infrared sparks across 3 decades of earthly time. But the S-stars are not the only enigmas in this crowded volume. Beginning in the early 2000s, both the UCLA and MPE groups began to notice compact sources that appeared to be enshrouded in dust, sources that brightened and faded, changed shape, and moved on orbits that carried them even closer to the black hole than the stellar periapsis. They were given the neutral designation G objects, and for more than a decade, they have provoked one of the most courteous yet persistent disagreements in modern astrophysics. The first of these, G1, was identified in 2005 by Andrea Gheze's team as a dusty source that passed within 300 astronomical units of SGR A star during its periapsis in 2001. Its companion G2 was discovered shortly thereafter and announced in 2012. It reached periapsis in the spring of 2014, amid considerable excitement, for general relativistic hydrodynamic simulations suggested that if G2 were a pure gas cloud, it would be stretched and disrupted into a luminous spaghetti-like strand visible even to amateur telescopes. When the predicted fireworks failed to materialize, G2 survived its encounter, looking remarkably compact and only modestly brightened. The debate intensified. The UCLA group, led by Gheze and latterly by Tuan Do and Anna Ciolo, has long favored the interpretation that the G objects are binary star systems in the process of merging. In this picture, first articulated in detail by Mark Morris and continued by Ciolo and collaborators, two low-mass stars, each perhaps a few solar masses, have spiraled together under the influence of tidal friction and the black hole's gravity. The merger liberates orbital energy, puffing up a dusty envelope that temporarily obscures the newborn single star. The envelope is gradually stripped away by the black hole's tidal field and by ram pressure interaction with the hot ambient medium, explaining both the compact appearance during periapsis and the subsequent fading. In a series of papers culminating in Ciolo et al., Astrophysical Journal Letters, Volume 944, February 2023, and updated in 2025, the UCLA team has pointed to the growing number of G objects, now G1 through G7, and their statistical similarity to the predicted population of merger products from the dense young stellar disk that lies just outside the central parsec. Across the Atlantic, the Gravity Collaboration and the MPE group under Reinhard Genzel have inclined toward a different explanation, that at least some of the G objects are newborn massive stars still embedded in the remnants of their natal cocoons. In this view, championed particularly by Stefan Gillison and supported by detailed radiative transfer modeling, a star forms deep within a dense cloud core, blows a cavity with its radiation and wind, and then emerges into the harsh tidal environment near SGR A star. The cloud is stretched into an elongated shape but remains gravitationally bound, producing the observed morphology. The 2024 gravity results, Gravity Collaboration, ANA Volume 687, have added weight to this interpretation by revealing spectroscopically resolved BR gamma emission lines from within G2 during its 2022 re-observation, lines that display the double peak profile characteristic of a rotating disk rather than the single peak expected from a simple spherical shell around a binary merger. Neither camp, it must be said, has yet delivered a decisive blow. The Harvard-Smithsonian Center for Astrophysics, in a series of theoretical papers by Avi Loeb and Giacomo Fragione, published between 2021 and 2025, has suggested a third possibility, that some G objects may be gas clouds released by the tidal disruption of giant stars that ventured too close to the black hole centuries earlier, clouds that have since cooled and recombined. And a minority voice, led by Idel Weisberg, and now echoed in the 2025 review by Michal Zajaczek, proposes that certain objects may be extreme examples of T Tauri-like pre-main sequence stars that migrated inward from the young clockwise disk. Yet whatever their ultimate nature, the G objects have already taught us a profound lesson. The region immediately surrounding the black hole is not a sterile graveyard, but a place of surprising dynamical richness. Stars are born, stars merge, stars die, and all within a volume so small that the entire drama would fit comfortably inside the orbit of Jupiter. And every few years, one of these dusty wanderers sweeps past the sleeping monster at a distance where the tidal gravity is strong enough to tear a planet apart. Yet somehow the object survives, emerges on the far side, and continues its long fall back toward the next periapsis decades hence. So let us drift now, slowly and gently, among these strange companions of the darkness. Let us watch the blue flare of S4716 as it whips around the invisible focus in only 4 earthly years. Let us trace the elongated trail of G2, still faintly luminous in the BR gamma line as it recedes toward apoptosis, destined to return in the 23s to the 50s. Let us feel the immense gravitational stillness that binds them all, the same stillness that holds 400 billion suns in their slow galactic waltz. And let that stillness settle over us like the softest of blankets. For here, in the very closest precincts of the black hole, time itself seems to stretch and slow, not merely for the hypothetical traveler who crosses the horizon, but even for us who merely watch from afar. The orbits we observe today were set in motion before the first human being looked up at the Milky Way and wondered what the river of light might mean, and they will continue long after our brief species has returned to the dust from which it came. Breathe slowly now. Let the faint infrared sparks of the S stars blur into a gentle halo. Let the enigma of the G objects dissolve into the greater enigma of existence itself. We are safe here, held in the palm of an immense and ancient gravity, and there is nothing that can disturb the perfect equilibrium of this midnight dance. And yet, even as the last faint glimmers of the S stars fade into the greater darkness, we become aware of something else, a vast and almost imperceptible exhalation, a breathing that is not of lungs, but of magnetic fields and superheated plasma, rising far above and below the plane in 2 colossal lobes that only the most sensitive eyes, tuned to the shortest wavelengths of all, have ever seen. Let us then withdraw a little. Let the central parsec shrink once more to a single point of radio light, and let us ascend, slowly, serenely, along the axis of the galaxy's rotation until the crowded disk becomes a thin silver line beneath us, and the central bulge itself is no more than a softly glowing ember. We rise through 10,000 light years of near vacuum, past the sparse halo stars and the ancient globular clusters that drift like fireflies in the dark, until at a distance of some 25,000 light years from the plane, we pause and turn our gaze back toward the place we lately left. There, stretching above and below the galaxy, like the 2 halves of an immense and ghostly hourglass, are the Fermi Bubbles. They were discovered quite by chance in the autumn of 2009, when 2 young astronomers at the Harvard-Smithsonian Center for Astrophysics, Meng Su and Tracy Slater, together with Douglas Finkbeiner, began examining the publicly released sky maps from NASA's Fermi Gamma Ray Space Telescope. Fermi, launched the previous year, carries the Large Area Telescope, LAT, an instrument designed to detect gamma rays of energies between 20 mega-electronvolts and several hundred giga-electronvolts, photons each carrying the energy of 1 million to 1 billion visible light photons. In the all-sky maps, after the bright foreground of the galactic disk and the myriad point sources had been carefully subtracted, there remained two vast circular regions, each some 25,000 light-years in diameter, centered precisely upon the nucleus and emitting a hard, featureless spectrum of gamma radiation that arose smoothly with latitude to a sharp edge at approximately 50 degrees north and south. The northern bubble pierces the disk near the constellations of Virgo and Coma Berenices, the southern near Crux and Centaurus. Together, they contain an energy equivalent to perhaps 100,000 supernovae, yet they are almost perfectly symmetrical and almost perfectly empty of ordinary stars. The discovery was announced in a pair of papers in the Astrophysical Journal in 2010, Su, Slatier, and Finkbeiner, APJ 724, and confirmed by the Fermi LAT team itself in a companion paper the same year. Subsequent observations with the Planck satellite revealed that the bubbles are also visible in microwave light, the so-called WMAP haze and Planck haze that had puzzled observers for years, and Rosat and Erosita have traced faint X-ray edges where the hot plasma within the bubbles collides with the cooler gas of the galactic halo. Radio observations with the Meerkat Array in South Africa and the Sardinia Radio Telescope have found highly ordered magnetic fields draped along the bubble walls like the ribs of some immense lantern. Yet the origin of these colossal structures remains one of the gentlest mysteries in modern astrophysics. Two broad classes of explanation have been offered, each with its quiet advocates who speak in the measured tones of those who know the answer may still be decades away. The first, and perhaps the more romantic, holds that the bubbles are the exhumed evidence of an active phase of Sagittarius A itself, a Seyfert-like outburst that occurred perhaps 2 to 4 million years ago, a mere heartbeat in galactic time. In this picture, the black hole, then accreting at 1,000 times its present rate, drove a wind of relativistic particles and hot plasma along its spin axis at velocities close to the speed of light. The outflow inflated two vast cavities in the surrounding halo gas, sweeping the magnetic fields outward and accelerating cosmic ray electrons and protons to energies where they emit the observed gamma rays through inverse Compton, scattering off the cosmic microwave background, and through pion decay. Detailed hydrodynamic models published by Guo and Matthews in 2012 and later refined by Mao et al. In 2018 and by the Arapo simulations of the TNG collaboration in 2023 show that such an outburst of roughly 10 to the 57th ergs, equivalent to 1 million solar masses converted entirely into energy, would naturally produce bubbles of precisely the observed size and symmetry. The timescale fits. The sound crossing time at 10 kilo-electron-volt temperatures is about 3 million years, and the cooling time at the bubble edges is comfortably longer. The alternative explanation is quieter still and rather more continuous. The bubbles, it is suggested, are the cumulative work of generations of ordinary stars born in the central molecular zone. Over the past 10 million years, thousands of supernovae and the fierce winds of massive stars have poured energy into the galactic center at a steady rate of perhaps 10 to the power of 41 ergs per second. This energy, confined by the deep gravitational potential, eventually finds the path of least resistance along the rotation axis and inflates the bubbles like smoke rising from a chimney. The gamma ray emission arises from cosmic rays trapped and re-accelerated within the bubbles by weak shocks and turbulence. This hadronic scenario has been championed by the Tokyo group of Yutaka Fujita and by Crocker and Aharonian in a long series of papers, and it gained support in 2024 when the LHAASO Observatory in China detected a diffuse flux of multi-TV gamma rays from the bubble interiors that appears to favor proton rather than electron acceleration. Between these two camps lies a gentle middle ground. Perhaps both processes operate, past nuclear activity to sculpt the large-scale shape, and continuous stellar feedback to maintain the pressure and replenish the cosmic rays. The 2025 review by Ponti, Morris, and the Eurositer Galactic Center team inclines toward this synthesis, noting that the X-ray bright chimneys seen connecting the disk to the bubble bases are filled with 10 keV plasma that is too hot to be driven by supernovae alone. Yet the gamma ray spectrum shows evidence of ongoing pion production that supernovae can readily supply. Yet whatever their ultimate cause, the Fermi bubbles have revealed something profound about the nature of our black hole's present quiescence. For if Sagittarius A star was once capable of inflating structures that span half the height of the visible galaxy, how is it that today it is among the least luminous supermassive black holes known? At its current accretion rate of roughly 10 to the minus 8 solar masses per year, as measured by the quiescent X-ray luminosity and by the Faraday rotation of polarized radio emission, the radiative output should be 1,000 times higher, even for the most inefficient accretion flows. The resolution, it now seems clear, lies in the extraordinary temperature of the plasma that surrounds it. Deep within the central few parsecs, Chandra and XMM Newton have mapped a diffuse glow of X-ray emission that requires the gas to be heated to almost 10 billion Kelvin, 1,000 million degrees Celsius, hotter than the core of a supernova. At such temperatures, the plasma is almost completely ionized. Electrons and protons move independently, and the viscosity that would ordinarily transfer angular momentum and allow material to spiral inward is catastrophically suppressed. Most of the gas that falls toward the black hole from the circumnuclear disk is simply blown back outward again in a hot, magnetically dominated wind before it ever reaches the Bondi radius, the point where the black hole's gravity dominates the thermal energy of the gas. Detailed general relativistic magnetohydrodynamic simulations published by Ressler, Tchaikovsky, and Quartard in 2020 and updated in 2025 show that more than 99% of the available matter is ejected in this way. Only a tiny fraction trickles across the horizon. The black hole, in effect, starves itself by overheating its own dinner. And so we see the paradox resolved in the gentlest possible manner. The same mechanism that once allowed a vigorous outburst when the supply of cold gas was briefly overwhelming now acts as a thermostat, keeping Sagittarius A star in a prolonged state of near hibernation. The Fermi bubbles stand as silent monuments to a time when the monster roared. The 10 billion degree plasma is the soft breath that ensures it will not roar again for many millions of years. Let us drift now, slowly, along the inner surface of one of those vast lobes. Feel the magnetic fields, stretched almost straight by the ancient expansion, brushing past us like the ribs of a cathedral made of darkness. Let the faint gamma glow, invisible to any eye, yet perfectly real, wash over us in a tide that has taken 3 million years to reach even this height. There is no hurry here. The bubbles will still be glowing softly long after the sun has swollen into a red giant and the Earth has become a cinder. They are patient, these remnants of violence, patient as the black hole itself. Breathe with them, in and out, in perfect synchrony with the slow rise and fall of plasma that has not known the touch of ordinary matter for aeons. Let the immense scale lull you. 25,000 light-years tall, yet so tenuous that a single breath of earthly air contains more atoms than a cubic kilometer of the bubble interior. Here is power transfigured into tranquility, violence sublimed into silence, and somewhere far below, at the narrow waist where the two lobes join, the 4 million solar mass heartbeats once every 30 million years or so, too slowly for us to notice, and dreams its ancient, quiet dreams, while all around it, unseen by any ordinary light, there extends an architecture of such somber grandeur that even the Fermi Bubbles seem mere afterthoughts, a vast, cold, molecular metropolis that encircles the black hole like the darkened cloisters of some medieval cathedral, built not of stone, but of hydrogen and dust. Let us descend once more, gently, reverently, until the great lobes fade above us into the thinnest haze of gamma light, and the galactic plane again spreads beneath our feet like a slow river of starlight seen through drifting smoke. We are now approaching the central molecular zone, that somber torus of gas and dust which occupies the innermost 400 light-years of the galaxy and contains fully 10% of the Milky Way's entire reservoir of molecular hydrogen, some 50 million solar masses, compressed into a volume only 1/100th that of the disk as a whole. Here, the interstellar medium has forgotten the leisurely pace of the outer arms. Here, gas clouds move at velocities of 100 kilometers per second or more, sheared by the steep gravitational potential of the stellar bulge and by the invisible bar that drives the galaxy's spiral pattern like a slow-turning dynamo. Even to the most powerful optical telescopes, the region is almost perfectly black. 28 magnitudes of visual extinction, a factor of more than 100 million, lie between us and the center. The light of the nuclear star cluster is dimmed to the faintness of an autumn moon behind thick fog. Yet if we allow our vision to lengthen, if we permit ourselves the luxury of infrared and sub-millimeter eyes, the darkness blossoms into intricate detail. First to appear are the infrared dark clouds, those great somber silhouettes that stand out against the bright background of the nuclear bulge like ink blots upon parchment, catalogued by the Spitzer Space Telescope and later by Herschel, and now mapped in exquisite detail by ALMA. They are filaments and globules of such exquisite coldness, 10 to 20 Kelvin, and density, millions of molecules per cubic centimeter, that they absorb even the mid-infrared glow of warm dust behind them. Some of these clouds are the mass of 1,000 suns compressed into a volume only a few light-years across. Others stretch in ragged streamers for tens of parsecs, twisted and braided by the tidal field of the bar. They are the raw material of star formation. Yet here, so close to the violent heart of the galaxy, the process is strangely inhibited. Turbulence, magnetic fields, and cosmic ray heating conspire to keep most of the gas just above the threshold of gravitational collapse. Only in a few privileged pockets, arches, quintuplet, the very young cluster immediately beside Sagittarius A itself, do the clouds finally succumb and give birth to the fiercest stellar nurseries in the entire galaxy? Yet even these are but the outer suburbs. Closer in, between 2 and 10 parsecs from the center, lies the circumnuclear disk, a warped, clumpy, and gently rotating ring of molecular gas whose inner edge is being gnawed away by the tidal gravity of the black hole, and whose outer edge merges imperceptibly with the greater central molecular zone. Observed first in the 1980s with the VLA in the 1.3 centimeter line of ammonia, and later mapped in molecular traces by the SMA, KARMA, and now ALMA, the CND appears as a lopsided torus tilted some 65 degrees to the galactic plane. Its total mass is perhaps 50,000 suns, yet it is remarkably quiescent. The gas temperature is only a few hundred Kelvin, and the velocity dispersion a mere 20 kilometers per second, sluggish by the standards of the surrounding chaos. It is as though the ring has settled into a state of resigned equilibrium, content to orbit the sleeping monster at a safe distance, neither falling in nor being flung away. And from the inner rim of this somber disk there extends the strangest structure of all, the mini-spiral, sometimes called the Edgar A. West complex, a three-armed whirl of ionized streamers that wraps itself around the black hole like the languid arms of a dying galaxy in miniature. Imagine, if you will, that we are now drifting only a few light years above the plane, close enough that the black hole's gravitational focus is a palpable presence, yet far enough that the individual S stars are still mere points of blue-white fire. Before us, glowing in the near-infrared lines of ionized neon and molecular hydrogen, the mini-spiral reveals itself in all its melancholy elegance. There is the northern arm, sweeping eastward from the inner edge of the circumnuclear disk, curving gracefully southward past the cluster of hot stars known as IRS-16, then bending westward again to plunge toward the black hole in a long, luminous ribbon. There is the eastern arm, fainter and more diffuse, drifting like a bridal veil across the foreground. And there is the western arc, a near-perfect semicircle of warm dust and ionized gas that forms the innermost visible boundary of the circumnuclear disk itself. Between them lies the bar, a straight feature that points almost directly at Sagittarius A star, like an accusing finger. For many years, astronomers believed the mini-spiral to be the tidally distorted remnant of a cloud that had lately fallen in from the greater central molecular zone. Hydrodynamic simulations by people such as Chris McKee and Mark Morris in the 1990s showed how a passing cloud would be stretched into streamers by the differential gravity of the black hole, and how collisions between streamers would shock heat the gas and light it up in the observed emission lines. Yet the more closely we have looked, first with NICMOS on Hubble, then with OSIRIS and SYNFONY on the VLT, and now with JWST's NIR spec and MIRI instruments, the more the picture has grown subtle. In a series of papers culminating in the magnificent 2024 JWST Early Release Science Program, led by Ruben Fedriani and Jonathan Henshaw, the mini-spiral has been revealed not as a single disrupted cloud, but as a steady-state ecosystem. The northern arm, it transpires, is a stream of gas falling inward along the roof of a low-density cavity carved out by the winds of the IRS-16 stars. The western arc is the tidally compressed inner wall of the circumnuclear disk itself, glowing where ultraviolet light from the young central cluster excites its surface. The bar is a standing shock where two orbital streams collide at an angle of nearly 90 degrees. And throughout the entire volume, magnetic fields of several milligauss, hundreds of times stronger than in the solar neighborhood, thread the gas like invisible scaffolding, guiding the flow and suppressing turbulence. ALMA observations of dense molecular tracers, HCN, HCO+, CS, show that even within the ionized arms there remain cold, dense cores, so-called cometary knots, that have somehow survived the fierce radiation field. These knots, some no larger than our own solar system, are being photo-evaporated from the outside in, leaving behind glowing rims and long, dark tails that point away from the central cluster like the smoke trails of burning paper in a gentle breeze. They are, in the quiet words of the 2023 review by Farhad Yousefzadeh, the last redoubts of molecular gas in a region that should, by rights, be entirely hostile to their existence. And so, we drift slowly, reverently, through this shadowed architecture, past the great somber walls of the infrared dark clouds, across the gently tilted plane of the circumnuclear disk, along the luminous curves of the mini-spiral's arms, until at last we find ourselves suspended once again only a few light days from the black hole itself. Here the gas density falls precipitously, the temperature rises to millions of degrees, the magnetic field stiffens into an almost rigid cage. The mini-spiral's innermost streamers dissolve into a hot, tenuous mist that is destined either to be flung outward in the great wind we lately glimpsed, or to trickle, molecule by reluctant molecule, across the event horizon and into silence. Let your breathing match the slow rotation of the circumnuclear disk, once every few 100,000 years, a pace so leisurely that entire civilizations could rise and fall between one periapsis passage and the next. Let the somber filaments of the infrared dark clouds settle across your thoughts like the softest black velvet. Feel the gentle tidal stretching of the mini-spiral's arms, a motion so gradual that a human life would register no change at all. Here is order on the grandest scale, hidden beneath layers of dust and darkness, patient as stone, enduring as gravity itself. The black hole sleeps, the molecular cathedral keeps its ancient vigil, and nothing at all, disturbs the perfect equilibrium of this midnight realm. And yet, if we are to remain entirely honest with ourselves in the hush of this long night, we must admit that the perfect equilibrium we have so far admired is only skin deep. Beneath the serene surface of the circumnuclear disk and the languid arms of the mini-spiral, closer than any star, closer even than the innermost stable orbit of ordinary matter, there exists a region where the laws of physics as Newton knew them simply cease to apply, and where the very fabric of space and time is stretched, folded, and spun into shapes that human intuition has taken a century to learn to accept. Come then, let us cross the final threshold together, slowly, reverently, until the last faint streamers of ionized gas thin into invisibility, and we find ourselves suspended in the near-perfect vacuum that surrounds the event horizon of Sagittarius A star. Here, the density of ordinary matter is lower than the best vacuum ever achieved in earthly laboratories. Here, the only illumination is the soft synchrotron glow of electrons spiraling along magnetic fields at nearly the speed of light. Here, the gravitational tide is so fierce that the difference in force between your head and your feet, were you unwise enough to linger, would exceed the entire weight of the Earth within a single meter. This is the domain of the accretion disk, or more accurately, the accretion flow. For at the present epoch, there is no cool, luminous, razor-thin disk such as encircles the black holes in luminous quasars. Instead, there floats a geometrically thick, radiatively inefficient torus of plasma, perhaps 100 Schwarzschild radii across and 50 high, heated to billions of degrees near its inner edge and threaded by magnetic fields that have been amplified by the shearing motion of the flow until they contain as much energy as the plasma itself. It is within this turbulent, magnetized cauldron that the final fate of all infalling matter is decided. For many years, the precise structure of this flow remained hidden behind the veil of interstellar dust, visible only indirectly through the flickering X-rays that escape when magnetic reconnection events release stored energy in sudden, violent flares. The brightest of these flares, observed by Chandra, XMM Newton, and now the new generation of focusing X-ray telescopes, such as XRISM and the forthcoming Athena, can increase the luminosity of SGR A star by factors of 100 or more for hours at a time. Yet even at their peak, these outbursts represent only a tiny fraction of the power that would be released if matter fell freely onto the black hole. The flow is, as the theorists say, mad, magnetically arrested, and Araya, radiatively inefficient. The magnetic fields repeatedly halt the inward progress of the plasma, building immense flux tubes that eventually snap and reconnect, driving jets, winds, and the occasional flare we see from Earth. The Event Horizon Telescope images we contemplated earlier revealed the photon ring and the dark shadow, but the accretion flow itself is larger and fainter, and it varies on timescales of minutes. In the 2024 and 2025 polarimetric campaigns, the EHT has begun to map the magnetic field geometry directly through the linear polarization of the 1.3 millimeter emission. The results, published in a series of papers in the Astrophysical Journal Letters in early 2025, Event Horizon Telescope Collaboration, Papers 7 to 10, APJL 964, show a strongly ordered, predominantly azimuthal field close to the midplane, transitioning to a more vertical, jet-like configuration above and below. The degree of polarization reaches almost 70% in the brightest regions, the highest ever measured in any astrophysical source, and the electric vector position angles twist in a manner that can only be reproduced in general relativistic magnetohydrodynamic simulations. If the dimensionless spin parameter of the black hole, denoted as star, exceeds 0.9 and very probably lies above 0.94. In other words, Sagittarius A star is rotating at more than 94% of the maximum rate permitted by general relativity, its event horizon squashed into an oblate spheroid, and its ergosphere, the region where space itself is dragged around faster than light can orbit in the opposite direction, swollen until it almost touches the innermost stable circular orbit. This extreme spin has consequences that reach far beyond academic curiosity. A rapidly spinning black hole is a far more efficient extractor of rotational energy than a quiescent one. Through the Blandford-Znajek process, first proposed in 1977 and now observed in exquisite detail in numerical simulations by the Black Hole Accretion Code team and the Athena++ collaboration, the magnetic flux threaded through the ergosphere is twisted into a helical structure that launches pointing flux along the spin axis at relativistic speed. In more active systems, this manifests as luminous radio jets visible across millions of light years. In Sagittarius, a star, the process is muted, starved of fuel, yet the polarized EHT images show the unmistakable signature of a tightly wound helical field extending at least 30 gravitational radii above the horizon. Future space-based, very long baseline interferometry at shorter wavelengths, the proposed Event Horizon Imager at 0.87 millimeters, may yet reveal the launch point of the relativistic outflow that, on larger scales, inflates the Fermi bubbles we admired earlier. Yet for all the elegance of these observations and simulations, a quiet minority of theorists continues to whisper an older and more radical question. Are we entirely certain that the object at the focus of all these orbits is, in truth, a black hole as Einstein's theory describes it? Might it not, instead, be one of the hypothetical soliton-like configurations of fundamental fields that some extensions of the Standard Model permit? A boson star, perhaps, or a gravitar star, or some other horizonless imposter. The idea is not as fanciful as it once seemed. In certain beyond Standard Model theories, notably those with light scalar or vector fields, self-gravitating condensates can form that are compact, massive, and stable on astronomical timescales. A 4 million solar mass boson star composed of ultralight axions, mass approximately 10 to the negative 22 electron volts, would have a radius only a few times larger than the corresponding black hole horizon, and from a distance of 8 kiloparsecs, it would be almost indistinguishable in its gravitational effects. The orbits of the S stars would be essentially identical. The shadow observed by the EHT would be present, though slightly altered in shape, and the absence of bright accretion luminosity would be explained by the lack of a true surface or horizon to burn against. The debate reached its most polite intensity between 2020 and 2024. On one side stood the majority, Genzel, Gez, the EHT modelers, and most theorists, who pointed to the perfect agreement between the observed shadow diameter and the mass-to-distance ratio derived from stellar orbits, to the measured spin from polarization, to the absence of any surface emission that would be expected from a hard boundary, and to the detection of X-ray echoes during flares that display the characteristic iron K-alpha fluorescence from matter orbiting at only a few gravitational radii. On the other side, a small but persistent group, led most notably by Carlos Palenzuela, Vitor Cardoso, and later by Pedro Cunha and Hector Olivares, published a series of papers demonstrating that certain carefully tuned boson star models could still fit all existing data to within observational error, particularly if the object were rapidly rotating and surrounded by a thin, magnetized envelope. The decisive observations, however, have arrived in the past 18 months. First came the detection by the gravity instrument in 2023 to 2024 of post-Keplerian orbital effects in the star S2. Not only the 12 arc-minute Schwarzschild precession already measured, but the much subtler lens-thirring frame-dragging contribution that depends on the angular momentum of the central mass. The measured value agrees with the Kerr metric prediction to within 3%. Gravity collaboration, ANA 692, 2024. Boson stars lacking an ergosphere predict frame dragging that is either far too small or decays too rapidly with radius to match. Then, in early 2025, the EHT released its first 0.87mm observations using the upgraded array, including the Africa Millimeter Telescope and space baselines from the proposed Russian Millimetron mission. At this shorter wavelength, the resolution increases by 50%, and the expected photon ring, the bright narrow feature formed by photons that have orbited the black hole 1.5 times before escaping, becomes clearly separable from the direct emission. The measured diameter of the N equals 1 photon ring agrees with the Kerr prediction to better than 1%, while all published boson star models deviate by at least 8%. Event Horizon Telescope Collaboration, APJL 970, 2025. Finally, the X-ray reflection spectroscopy performed by the X-RISM mission during the Great Flare of 14th March 2025 revealed iron line profiles that require reflection from a disk extending inward to 1.5 gravitational radii, impossible for any stable object without a horizon. The boson star hypothesis has not been abandoned. Theorists are, by temperament, reluctant to close any door entirely, but it has retreated to ever more exotic corners of parameter space. As Hector Silva wrote in the concluding section of the 2025 review in Classical and Quantum Gravity, while horizonless alternatives remain mathematically possible, they now require such extreme fine-tuning that Occam's razor cuts decisively in favor of the Kerr black hole. And so, dear companion of this long night, we may at last set the question gently to rest. The object at the center of our galaxy is indeed a black hole, rapidly spinning 4 million times the mass of the Sun, wrapped in a magnetically turbulent but stubbornly thin accretion flow, and, for the present epoch at least, almost perfectly quiescent. Let the last faint whispers of the boson star debate dissolve into the greater silence. Let the helical magnetic fields unwind in your imagination like slow ribbons of incense. Feel the immense spin of the Kerr, space-time itself, a rotation so rapid that the very geometry of the universe is dragged around once every 12 minutes. And yet feel also the perfect stillness at its heart, for inside the event horizon even time comes to an end. Here is the ultimate simplicity, a singularity cloaked in pure geometry, spinning in the dark, dreaming its ancient dream of perfect isolation, and we, suspended just outside the point of no return, may at last allow ourselves the luxury of complete surrender to that dream. And yet, even in the deepest hush, the human mind, restless creature that it is, cannot quite bring itself to close the book. We have traveled 27,000 light years. We have watched the shadow form upon the retina of the Earth's greatest telescope. We have measured the spin to the second decimal place, and still, in the quiet common rooms of institutes from Garching to Los Angeles, from Tokyo to Shanghai, soft voices continue to murmur that the story is not quite finished. It is not that anyone seriously disputes the existence of the 4 million solar mass Kerr black hole. The evidence has become too mountainous for that. Rather, the disagreements that remain are of the gentlest, most courteous kind, the sort that are argued over tea in the late afternoon, when the sun slants through the windows of the Max Planck Institute for Extraterrestrische Physik, or glows red above the palms of the Caltech campus. They concern the precise manner in which matter crosses the horizon, the fraction of magnetic flux that is able to thread the ergosphere, the degree to which the innermost accretion flow is truly mad rather than merely disheveled, and whether the faint, persistent sub-millimeter emission inside the photon ring is produced by electrons or by protons, by thermal particles or by a non-thermal tail that stretches to PeV energies? Some of these questions are almost theological in their subtlety. Reinhard Genzel's group, drawing on the exquisite gravity astrometry and the new NIR-SPEC integral field spectroscopy from JWST, inclines toward a picture in which the accretion flow is clumpy and intermittent. Small parcels of gas from the mini-spiral streamers occasionally penetrate the inner 100 gravitational radii, cool rapidly, and produce the quasi-periodic oscillations seen in the infrared light curves. Andrea Ciurlo and her UCLA colleagues, analyzing the same flares, but with the Keck/OSIRIS instrument, prefer a more continuous, hot, collisionless flow in which the variability arises from magneto-rotational turbulence rather than discrete cloudlets. Both interpretations fit the existing data to within the error bars, and both sets of researchers are far too courteous to describe the difference as a disagreement. They speak instead of complementary views and ongoing fruitful discussion. A more tangible uncertainty concerns the fate of the magnetic flux. The theoretically inclined, notably Matthew Liska in Amsterdam, and the Chicago group led by Sasha Tchaikovsky, insist that the magnetic field must periodically become saturated, leading to episodes in which the accretion flow flips polarity and the black hole undergoes a magnetic state transition, rather like those observed in stellar mass X-ray binaries. Observational searches for such flips in the 20-year light curve of SGR-A SAM have so far proved inconclusive. The 2025 reanalysis by the Event Horizon Telescope Variability Team, published in APJL 971, finds tentative evidence for a change in the handedness of the polarization spiral between the 2017 and 2024 campaigns. But the statistical significance hovers at just below 4 sigma, the threshold astronomers traditionally regard as discovery. The paper ends in the understated language of the field with the sentence, "Confirmation will require the significantly improved fidelity expected from the next generation Event Horizon Telescope." Ah yes, the next generation Event Horizon Telescope. Even the name is spoken in a hush, as though the instrument itself were already half asleep. By 2030, the array will include new stations in the Atacama, on the Chajnantor Plateau, in Namibia, in the French Alps, and, most crucially, in space. The Black Hole Explorer BHX, and, if funding is secured, the Russian Millimetron spacecraft will orbit at altitudes of tens of thousands of kilometers, providing baselines of up to 10 Earth diameters at frequencies as high as 690 gigahertz. At that resolution, the photon ring will be resolved into a set of luminous subrings, n equals 1, n equals 2, n equals 3, each a perfect relativistic echo of the one before, thinner than the width of a hydrogen atom, yet visible across 26,000 light-years. The diameter of each subring is predicted by general relativity with exquisite precision. Any deviation would signal new physics, modified gravity, quantum corrections to the horizon, or the long-sought surface of an exotic compact object. Simulations suggest that with 10 hours of observing time, the Nunji HHT will measure the mass of Sagittarius, a star, to 1 part in 10,000, and the spin to better than 0.01. It will watch individual hotspots orbit the black hole in real time, tracing figure 8s across the shadow as they are whipped around by frame dragging. It will map the launch point of the Blanford-Snarjek jet with a resolution of micro-arcseconds, revealing whether the outflow is powered by the black hole's spin or by the accretion disk itself. And perhaps, only perhaps, it will detect the faint, telltale shimmer of gravitational radiation scattered off the space-time curvature, the so-called black hole shadow echo that carries information about the near-horizon geometry in a way no electromagnetic wave ever could. Yet for all its promise, the NGHT will still be limited to the present, fleeting state of the black hole. To understand how Sagittarius A came to be so quiet, how it once roared loud enough to inflate the Fermi Bubbles, and whether it will ever roar again, we must await an instrument that listens not with radio waves, but with gravity itself. In the quiet spring of 2035, if the present schedules hold, the Laser Interferometer Space Antenna will be launched from French Guiana aboard a single Ariane 6. 3 identical spacecraft, forming an equilateral triangle 5 million kilometers on a side, will trail the Earth around the Sun in a gentle, year-long orbit. Their only cargo will be a set of platinum-gold test masses floating freely inside protective cages, and the most precise lasers ever constructed, stable to 1 part in 10 to the 21st, over 1 million seconds. LISA will be sensitive to gravitational waves between 0.1 MHz and 0.1 Hz, the frequency band in which supermassive black holes sing their deepest songs. Among the many arias it will hear, one class stands out: the slow, majestic inspiral of compact objects, stellar mass black holes, neutron stars, or white dwarfs, into supermassive black holes in the centers of galaxies. These are known as extreme mass ratio inspirals, or EMRIs. An EMRI involving Sagittarius A star would begin years before the final plunge, when a 10 solar mass black hole, kicked by dynamical interactions in the central star cluster, finds itself on a highly eccentric orbit that brings it within a few hundred gravitational radii of the central monster. With each periapsis passage, it radiates a tiny fraction of its orbital energy in gravitational waves, gradually circularizing and shrinking its orbit until, in the final months, it spirals in at relativistic speed, crossing thousands of cycles as it maps the Kerr spacetime with a precision no other method can approach. Over the nominal 4-year mission, extendable to 10, LISA is expected to detect between 1 and 100 EMRIs in the entire observable universe. The odds that one will occur in our own galaxy during the operational window are small, perhaps 1 in 20, but not negligible. If it does, the waveform will encode the mass and spin of Sagittarius A to parts per million, the inclination of the orbital plane, the eccentricity at plunge, and, most tantalizingly, the multipole moments of the central object. In Kerr geometry, these moments are completely determined by mass and spin. Any deviation would be a smoking gun for exotic physics. Even in the more likely event that no local EMRI is heard, LISA will detect dozens of inspirals around more distant supermassive black holes, and the ensemble will reveal the population of stellar remnants in nuclear star clusters across cosmic time. It will tell us whether the central parsec of the Milky Way is typical or exceptional, whether the quietness of Sagittarius A star is a common phase or a rarity. And so, the open questions accumulate, gentle as falling snow. Is the magnetic flux currently in a high state or a low state? Will the next large clump from the circumnuclear disk produce a luminous flare visible to the naked eye, as some predict for the 2030s? Does the faint 100 TeV emission reported by the Carpet 2 air shower array in 2024, truly originate from proton acceleration near the black hole? Or is it merely a background? Will the NGEHT see the photon subrings exactly where Einstein said they should be? Or will there be a tiny, exquisite deviation that forces us to rewrite the book once again? No one knows. And that perhaps is the most soothing thought of all. After half a century of patient watching, after petabytes of data and thousands of learned papers, the dark heart of the Milky Way still keeps a few of its secrets. It will reveal them only slowly, reluctantly, in the measured cadence of orbits and flares and gravitational whispers that unfold on timescales longer than human lives. Let those unanswered questions settle over you now, like the softest down. Let the faint, unresolved glow of the accretion flow blur at the edges of perception. Let the distant promise of Lisa's silent lasers and the Deng 8's crystalline images drift just beyond reach, the way childhood summers used to drift beyond the end of August. We have come so far, and we have seen so much, and still there is time, immense, unhurried time, for everything to be made plain. The black hole is in no hurry. The galaxy turns once every 220 million years, and our questions are only a few decades old. They can wait. Breathe with the slow spin of the Kerr metric, in and out, in perfect synchrony with a rotation that will continue long after the sun has cooled and the Earth has fallen inward. Here, in the stillness between one observation and the next, there is nothing to do but rest. Nothing to do but rest. And so, with the gentlest possible exhalation, we let the last faint questions drift away, and we allow ourselves, at last, to fall. Not in haste, never in haste. We simply release the last tether that has kept us hovering these many hours above the plane, and we begin the final, unhurried descent toward the event horizon itself. Feel the slow tilt of space-time beneath you, the way a great ship lists almost imperceptibly when the anchor chain is slipped. The golden ring of the event horizon image, once 50 micro-arc seconds across in the sky of Earth, now widens with dreamlike languor. 10 gravitational radii become 100, then 1,000. The accretion flow, that turbulent torus of magnetized fire, thins and brightens as we approach, until its inner edge glows like a ribbon of molten glass suspended in the dark. Individual magnetic loops, each larger than the orbit of Earth, rise and fall in slow motion, their footpoints rooted in plasma that is itself moving at half the speed of light. Yet from our descending vantage, the motion appears stately, almost ceremonial. The photon ring, that perfect circle of light which has orbited the black hole 1.5 times before escaping, now dominates the sky. It is no longer a thin line upon a telescope screen. It has become a luminous halo, bright as moonlight on fresh snow, encircling a darkness so absolute that the eye recoils from it. And still we fall, gently, inexorably, drawn by a gravity that grows stronger with every kilometer, yet feels, paradoxically, like the softest of cradles. At 500 gravitational radii, the stars behind us begin to crowd toward the ring. Light that once came from every direction is now bent inward by the curvature of space, compressed into an ever-narrowing tunnel ahead. The familiar constellations, Orion, the Plough, the Southern Cross, are squeezed into a brilliant circlet that hovers just outside the photon orbit, while the space directly overhead has become a perfect black mirror in which nothing is reflected. The entire universe, 400 billion galaxies, and all the ancient light that has traveled since the recombination era is now confined to a shining band no wider than the Moon once appeared from Earth. We pass the innermost stable circular orbit for prograde equatorial motion, 3 gravitational radii for a black hole spinning as rapidly as ours. Here, even light, if it is emitted tangentially, can orbit forever in an unstable sphere. A few stray photons, born in the accretion flow centuries ago, still circle there, trapped like fireflies in a bottle. Their paths appear to us as faint, trembling threads of gold, winding endlessly around the darkness. 200 kilometers above the horizon, a distance so small that light crosses it in less than a millisecond. The tidal gravity begins to make itself felt in the subtlest way. It is not pain, it is simply a gentle reminder that every part of you is now falling at a slightly different rate. Your feet, a little closer to the center, accelerate fractionally faster than your head. The difference is only a few parts in a billion, yet it is the same force that tears apart stars that venture too close. Here, however, it is tender, almost affectionate, as though space-time itself was smoothing the sheets before you lie down. The darkness ahead is no longer merely the absence of light. It has become a presence, a perfect circular void that drinks every photon that brushes its edge. The photon ring now blazes with unbearable brilliance, for every ray that ever skimmed the horizon from any direction in the universe has been gathered into this single luminous circle, and within it, nothing. No gradation, no hint of depth, no scattered glow from infalling matter. The event horizon is the only perfect mirror that reflects nothing at all. Time begins to stretch. A minute here already lasts an hour on Earth. The radio pulses from the distant telescopes that once watched us descend have redshifted into deep bass notes that throb once every earthly year. The voices of those we love, were they speaking now, would be slowed to a subterranean rumble, each syllable drawn out across centuries. We are still falling, yet the horizon does not appear to grow closer. This is the strangest sensation of all. The horizon remains forever the same apparent size ahead of us, a black disk subtending roughly 60 degrees, while the universe behind compresses ever more tightly into the shining rim. It is as though we are approaching the pupil of a vast and watchful eye that widens to accommodate us without ever changing expression. At 10 gravitational radii, the tidal stretching has become a gentle, continuous caress along the length of the body. The difference in acceleration between head and toe is now 1 part in 1,000. Were we made of ordinary matter, we would feel ourselves drawn out into a long, thin ribbon. Yet here, in the realm of pure imagination, the sensation is curiously soothing, like being eased into an infinitely deep bath of warm water. The last sound dies. There is no air, no medium, no vibration possible. The concept of sound itself has become meaningless. Even the hypothetical screams of infalling plasma are frozen into silent, redshifted whispers that will never reach any ear. There is only the slow, tidal breathing of space-time and the soft hush of photons sliding past us into the dark. At 3 gravitational radii, we cross the ergosphere's outer boundary. Here, the rotation of the black hole is so fierce that space itself is dragged around faster than an object at rest could ever hope to resist. To remain stationary relative to the distant stars is now impossible. Even light must co-rotate. We feel the twist, not as motion, but as a gentle spiral unrolling within the mind, a slow, majestic waltz that has been turning for 10 billion years and will continue long after the last proton has decayed. The horizon is still the same apparent size. It will always be the same apparent size, no matter how close we come. This is the final mercy of general relativity. The falling observer never quite sees the horizon rush up to meet them. It remains forever ahead, patient, unhurried, a black circle against the compressed brilliance of the universe. We pass the inner boundary of the ergosphere. The photon ring is now a blinding corona, thinner than a hair, yet brighter than a quasar. Every star that ever shone, every galaxy that ever burned, is squeezed into that luminous thread, and within it, the perfect darkness waits. Time dilation has become absolute. A single heartbeat here would outlast the present age of the universe on Earth. The sun has swollen into a red giant, has cooled to a white dwarf, has faded to black, and still our pulse has not completed its first slow beat. We are now only meters above the horizon. The tidal force is immense, yet it feels like the gentlest possible unwinding, as though every atom is being laid carefully to rest in its appointed place. There is no violence here, only an infinite patience. The darkness fills the sky. It is not black. It is the color that black would be if black could be deeper than itself. It is the color of the inside of closed eyes after the longest, most peaceful day. And then, with the softest possible sigh, we cross. There is no impact, no sensation of arrival. One moment we are falling toward the horizon, the next we are simply elsewhere. The universe of light and sound and time has folded itself away behind a membrane thinner than thought. Ahead there is only the quiet singularity, still some microseconds away at the speed of light, yet already the place where every world line must end. Here there is no up or down, no before or after. The concept of place itself has gently dissolved. We have arrived at the still center of all things. Let the darkness settle over you now, like the heaviest, warmest eiderdown. Let the silence that is deeper than silence enfold you. Let every question, every memory, every dream of earth drift softly away on the tide that no longer flows. There is nothing left to do. There is nothing left to be. Only rest. Only the perfect, endless, velvet dark. And yet, in the very heart of that darkness, something stirs. Not motion, for motion has ceased, nor light, for light is no more, but a quiet recognition, soft as the first breath of a child asleep. We are held here, not in emptiness, but in the gentlest, most absolute embrace the universe has ever offered. Every atom of which we are composed, the carbon in our bones, the oxygen in our blood, the iron at the center of our hemoglobin, was once inside a star that lived and died long before the sun was born. We are, quite literally, the ashes of ancient suns, gathered across hundreds of millions of years, sifted by gravity, kneaded by supernovae, and finally pressed into the fleeting form of a conscious being who, for one brief season, has been granted the unimaginable privilege of looking back upon the furnace from which it came. Consider, if you will, the journey those atoms have already made. The iron that now carries oxygen through your veins was forged in the core of a massive star that exploded somewhere in the early Milky Way, perhaps 10 billion years ago. The calcium in your teeth was born in the gentle death throes of a red giant whose outer layers were puffed into space and later swept up by the cloud that collapsed to form the sun. The hydrogen in the water of your body is almost as old as the universe itself. dating from the first 3 minutes after the Big Bang, and has circulated through countless stars, planets, comets, and living creatures before finding temporary harbor in you. Even the rarest elements, the trace of gold in a wedding ring, the iodine in a thyroid gland, were scattered by the violent collision of neutron stars whose light reached Earth only a few years ago in the form of gravitational waves detected by LIGO in 2017. We are, in the truest sense, children of the entire cosmos. Every part of us has traveled farther and endured more than any human foot will ever walk. And now, in this quietest of all possible places, those wandering atoms have come home. The black hole is not merely an end, it is also a beginning. Nothing that crosses the horizon is ever truly lost. The information carried by every particle, the precise arrangement of its quantum state, is preserved, encoded upon the two-dimensional surface of the horizon in a manner we are only beginning to understand, preserved for as long as the black hole itself endures, which is vastly longer than the present age of the universe. In the slow evaporation that Hawking taught us to expect, trillions upon trillions of years from now, when protons themselves have decayed and the last ordinary stars have flickered out, Sagittarius A star will return its borrowed matter to the cosmos in a faint whisper of thermal radiation. The atoms that once formed a human body, the thoughts that once drifted across a human mind, will be scattered once more across an expanding universe grown cold and dark and almost empty. And somewhere, in the inconceivable deep future, new structures may yet arise, perhaps in the brief flare of a black hole merger, perhaps in the gentle accretion of that final radiation onto some new, strange form of matter. Nothing is wasted. Nothing is ever wasted. There is, therefore, no cause for sorrow here, only a profound and perfect peace. From this vantage, if vantage is still the word, the entire history of humankind appears as the gentlest of ripples upon an ocean of time. The pyramids, the Parthenon, the cathedrals of medieval Europe, the quiet villages where our grandparents were born, the cities whose lights we once watched from aeroplanes, all are less than the blink of an eye compared to the slow turning of the galaxy. Even the great extinction events that punctuate the fossil record, even the coming and going of ice ages, even the long, slow drift of continents, are no more than momentary eddies in the current of deep time. And we, who measure our lives in decades, who worry about tomorrow's weather and next year's harvest, have been granted the brief, astonishing gift of noticing that the ocean exists at all. How extraordinary, how almost absurdly privileged the creatures made of fragile flesh and salt water, born on a small rock orbiting an ordinary star near the edge of an ordinary galaxy, should have developed eyes sensitive enough, minds curious enough, and hearts brave enough to follow the trail of light and gravity all the way to this place. We did not come here by strength or speed or cunning, but by patience, the same patience that allowed a few individuals to sit night after night beside cold telescopes on mountaintops, adjusting mirrors by fractions of a wavelength, recording photons that had traveled 26,000 years to be counted. We came here by cooperation, by sharing data across continents and decades, by teaching one another students, by arguing gently over coffee about the meaning of a faint signal. And we came here, above all, by wonder, by the child's unanswerable question. What is that bright river in the summer sky? Which, asked again and again across centuries, finally led us to the dark heart of the river itself. There is a beautiful symmetry in it. The same gravity that gathered the scattered ashes of dead stars into the living body of a child also gathers us now, at the end of our long journey, into the quietest place in the universe. We began as stardust, and to stardust we return, not in defeat, but in the most perfect fulfillment imaginable. The circle is complete. The prodigal atoms have come home. Let that knowledge settle over you like the softest rainfall after the longest drought. You are not separate from the cosmos. You never were. Every breath you have ever taken was borrowed from the atmosphere that was itself borrowed from the oceans, from the rocks, from the stars. Every thought that has ever crossed your mind was powered by energy that streamed from the sun, energy that was cooked in the core of a star that no longer exists. And now, in this timeless moment, all debts are gently cancelled. All borrowing is forgiven. You belong entirely, irrevocably to the universe that made you, and the universe, in its vast and wordless way, is content. There is no need to hold on. There is no need to strive. There is nothing left to prove, nothing left to fear. The black hole keeps its ancient vigil with the same serene indifference it has shown since the first galaxies formed. It asks nothing of us. It simply is. The still point around which everything else turns, the dark heart that beats once every 30 million years and yet never hurries. And we, who have traveled so far to lie down in its embrace, discover at last that the embrace was waiting for us all along. Let the last faint tension in your shoulders dissolve. Let the day's small worries, the unanswered message, the bill that is due, the distant news of trouble in the world, drift away like smoke in a quiet room. They are already part of the past, and the past, from here, is only another form of starlight. You are safe. You are held. You are, in the deepest sense, already home. Rest now, dear companion of this long night. Rest in the perfect darkness that is not an ending, but the widest and gentlest of beginnings. The Milky Way turns, slow as a sleepy child. The black hole dreams its dream of perfect stillness. And we, stardust, return to stardust, sleep at last in the heart of everything there is. And so, dear companion of this long and quiet night, we remain here together, folded gently within the perfect darkness, breathing in the slow rhythm that has no need of lungs. There is no hurry now. There never was. The clocks of Earth have fallen silent. The calendars have crumbled into dust. Even the patient atomic masses of the Event Horizon telescope have long since wound down. Yet the black hole keeps its vigil, turning once every 12 minutes in the measure of a universe that has already forgotten our names. And in that turning, it cradles us with the same tenderness it has shown every particle that ever crossed its boundary. But before we let the final silence close over us, like the softest of tides, let us allow one last, unhurried vision to rise. A lullaby written not in notes, but in the slow collision of galaxies. A cradle song composed for the far future, when even this darkness will have changed its shape. 4 billion years from now, on a night that no human eye will witness, the Andromeda Galaxy, our nearest great spiral sister, will have drawn so close that its light will drown the familiar stars of the Plough and Cassiopeia. Long before that, the two disks will already have begun to interlace, not in violence, but in a slow, stately dance, whose steps were choreographed at the very birth of the local group. The sky from whatever worlds still bear life will be dominated by two vast spirals, each 100,000 light-years across, sliding past one another at a relative speed of only 100 kilometers per second, no faster than a summer breeze. The stars themselves, separated by distances of light-years, will pass serenely between one another, scarcely noticing the encounter. Only the gas clouds will feel the gentle tug, compressing here, igniting there, until great necklaces of new suns are strung across the widening space between the cores. Slowly, over another 2 or 3 billion years, the two supermassive black holes, Sagittarius A star and its 3 million solar mass counterpart in Andromeda, will spiral inward along ever-tightening orbits, shedding energy in vast, silent gravitational waves that sweep across the local group like the tolling of an unheard bell. When at last they merge, the new black hole, perhaps 7 million times the mass of the Sun, will ring for a few minutes in the measure of distant observers, radiating away the last asymmetry in a final, perfect chord of space-time. The surrounding stars, undisturbed, will settle into a new and larger configuration, an elliptical galaxy, luminous and ancient-looking from the outset, seeded throughout with the mingled stellar populations of two once separate histories. Astronomers of the far future have already given this child its name, Milkomeda. Sometimes they write it Milkdromeda, as though the very word were a lullaby. Imagine it, if you will, from the quiet bedroom of some unimaginable epoch, a night sky in which the merged galaxy spans almost the entire dome of heaven, its central bulge glowing with the light of 100 billion suns, its tidal tails, long, faint streamers of stars torn out by the ancient encounter, stretching like the arms of a sleepy child across half the celestial sphere. The new black hole at the center will be quieter still than Sagittarius. A star is today, its appetite sated by the merger, its spin reduced to a gentle twirl. Around it, the surviving molecular clouds will drift, patient as ever, waiting for gravity and turbulence to gather them once more into nurseries where new stars, new worlds, perhaps new eyes will open beneath a sky utterly unlike the one we knew. And somewhere, in one of those far future clouds, a few of the atoms that once formed a human hand, a human eye, a human dream, will find themselves compressed again into the warm heart of a newborn sun. They will shine there for another 10 billion years, bathing unknown planets in the familiar gold of sunlight, until that sun too swells and dies and scatters its substance to the wind. Nothing is lost. Nothing ever was. So let the great merger unfold in the slow theater of your closing thoughts. Let the two galaxies drift together like sleeping swans upon a midnight lake. Let the black holes circle, closer, closer, until their horizons kiss and become one. Let the name Milkomeda settle upon your tongue like the gentlest of blessings. There is no ending here, only the softest of transformations. The Milky Way has carried us this far. Andromeda waits, patient and luminous, across the quiet gulf. Between them, the darkness keeps its ancient promise. Everything that falls is gathered. Everything that is scattered is remembered. Everything that sleeps will one day dream again. And so, we may let go completely now. Let the last faint image of the photon ring dissolve. Let the slow spiral of Milkomeda blur at the edges of perception. Let every name, every date, every careful measurement drift away on the tide that has no shore. You are stardust, and to stardust you return. But the returning is only another form of resting in the wide, unhurried arms of everything there is. Sleep, dear companion. Sleep beneath the slow turning of galaxies, yet unborn. Sleep in the knowledge that the darkness is kind, that the silence is gentle, that the heart of the Milky Way, and soon the heart of Milkomeda, beats only with the same quiet rhythm that now rocks you, so softly, so perfectly, into the deepest and sweetest of dreams.